Hello everyone. Today we're going to talk about computational complexity. That is the study of all possible algorithms for a given problem. And also we're going to talk about the computational complexity analysis that is trying to find a lower bound for all possible solutions for a given problem. So we're going to start with the insertion sort and sorting. So here is one like pseudocode for the insertion sort, and for the sake of simplicity, we chose like the index, the first index as 1 and not 0. So here we have like an array S, and we have a number that is the number of items that we have in the array S, that is n. So that's the algorithm for I equal to 2 to I less than equal to n, that n is the last item in the array. So we are comparing every item that is on the lower index of the some number x that is at location s at location I, the array s at location I. Then if it's like the number that we are comparing is bigger than the x or item at location I, then we are like moving everything to the right. Okay, moving to the right, and at the end we are swapping the value at location j plus 1 with x. So that's a pseudocode for the insertion sort, and I know that you're all are familiar with this algorithm. So what I'm going to do is I'm trying to find the worst case time complexity for the comparison. Okay, so here when we are talking about the time complexity or like the complexity of an algorithm, okay, you can see that which one is like the main operation. So here, assume that our main operation is comparison of this value at location j with the value at location I that was x. Okay, so if we see this one as the like a main operation, so we can analyze the worst case and also the average case. So next, I'm going to do the like analysis on the worst case. Okay, so let's see that how we can find the what's it going to be time the worst case time complexity. Okay, for the number of comparison in the insertion sort. Okay, so assume that let's see that how it goes. Okay, but having some intuition into the problem. When I is equal to 2, okay, so the j is at maximum is 1, and we have this while loop running until the j, one of the condition is that j is going to be greater than or equal to 0. So for having the worst case is that all of the values at location j, they are going to be greater than x. Okay, so they are greater than x. So when I is equal to 2, okay, the number of comparison that we have, so let's write it here. So let's say that I is equal to 2. Then when j at maximum gonna be at first is 1, and there is no other time for j because j should be greater than 0, so only 1. So when I equal to j equal to, we have only one comparison. Okay, so when I is equal to 3, okay, so I is equal to 3, j can be 2 and 1. Okay, as you see, when j is equal to 2, there are two i's. Okay, so it's going to be 2. So this gives us a intuition that when I is equal to 2, we have one comparison. 1 is equal to 3, 2, and definitely when I is equal to 4, we'll have 3 comparison. So, and I goes up to n. So we can create a sigma here. So the number of comparison, the worst case, okay, we're going to be when I is equal to 2 to n, and here we'll have I minus 1. Okay, so when we have I equal to 4, we have 3. If we calculate this number, it's going to be n multiplied by n minus 1 divided by 2. So that's going to be the the worst case time complexity for the number of comparison in the insertion sort. Okay, and it's really easy to see that as I showed that how this works. Now we're gonna next we're gonna do the average case okay time complexity for the number of comparison for insertion sort. Okay, so let's do some tests. Okay, when with some example, we're gonna see that what's gonna be the average case time complexity for when we have the comparison in the insertion sort. So let's pick some I here. We are picking this, and I is equal to 3 here, and again we started with index 1. Okay, as the first index. So j will be these like index equal to 2, and also when j is equal to 1. Okay, as you see that. So there will be some cases. Okay, one case is that the item at location I equal to 3, that we call it as x, okay, is not less than all items that we are like comparing with all previous j's. Okay, so if this is the case, item at location I equal to 3 is going to stay at its location. So here, if x stays at location I, the number of comparison going to be 1. Let's say that, okay, the x, like the value location I, okay, gonna stay at location I minus 1, that is here. Okay, it's gonna go and see here. Okay, the case that this number that we have here, okay, is less than this one. Okay, not this example, but as general. So when item stays at goes to I minus 1, then the number of comparison is 2. Okay, so why we are saying item number of comparison is equal to 2? Because your first comparison with this item, then this item, and because this is not, let's say that this item that we have here, okay, is not less than the item of x. Okay, so we are not, this is going to go out of the while loop, because it goes out of the while loop, so we are only doing 2 comparisons. So we can continue this one. Okay, when x will sit at location I or I minus 1, when it's at location 2, this is I minus 1, and when also is the location 1 is also I minus 1. And the reason that these numbers are equal to each other is because in the while loop that we have, the like the condition was j should be like greater than 0. Okay, and because on the last one, okay, there is like the j will be equal to 0, so we are not doing j I minus 2 comparison. Okay, so that's the reason. I comparison, not I minus 1, I comparison. So, and now we have these like these are the averages, but also there is a probability of seeing this like situation. Okay, so it one, for having the average, okay, for doing the average, we're assuming that there's unlikely that any of these gonna like have the higher priority compared to others. Okay, so we are assuming that the probability of occurring all of these like situation gonna be same. So we have like 1 to I cases. Okay, so it means that the item that we have here gonna stay at this location or here or here. So we have 3 cases, and the situation that item at location I gonna stay as location or I minus 1 or I minus 2, okay, is gonna be same. So the probability of each of these gonna be 1 divided by I. 1 divided by I, 1 divided by I, and 1 divided by I. So again, if you look at this example that we have here, when I is equal to 3, okay, and we are gonna see that what's gonna be the like the average probability, okay, when there's no bias, like the numbers are like there's not in a condition that's gonna have more probability for all of them. So the probability of having the item number at location 3 be here or here or here are equal to each other. So that is equal to 1 divided by 3. That is 1 divided by I. Now for doing the average case, we are simply, okay, like based on the probability 3, we have this one. So we have 1, this is the number of comparison. Okay, so that was the number of comparison. So number of comparison 1, okay, that's going to be multiplied by 1 divided by I. Here we have 2, okay, multiplied by 1 divided by I, plus 3 multiplied by 1 divided by I, and until we go to I minus 1 divided by 1 multiplied by 1 divided by I, plus I minus 1 multiplied by I divided by I. So that's gonna be like the average one for for an item at location I. Okay, so if we sum these all numbers together, okay, so this will be equal to the summation of I equal to, let's say call it k, so k equal to 1, okay, and k goes to I minus 1 of k, okay, and plus I minus 1 divided by I, and here we have 1 divided by I. So let's have it here. It's gonna be k equal to 1, and here 1 divided by. So together, this equal to I plus 1 divided by 2 minus 1 divided by I. So, you know, I just like the simple math to see that this is going to be the number. Here, the number that we have, okay, is the average case for a number at location I, okay, but I can be from item 2, okay, from number 2 to n, okay. So if you look at the algorithm again, it was saying that I goes from 2 to number n. So we need to create another sigma. So our solution gonna be here. So let me erase the board. Gonna be the sigma of I equal to 2 to n, and this value that we have here, I plus 1 divided by 2 minus 1 divided by I. And if you just do the math, okay, you do the math, so if, you're gonna see this value that is gonna be in 2 divided by 4, okay. Okay, so we talk about the worst case and also the average case, some complexity of number of comparison for the insertion sort. And now we're gonna talk about the analysis of like the space complexity of the insertion sort. So as you saw, like the algorithm, like the pseudocode, you saw that we didn't use like too much like extra spaces, and all those like variables that we use, like such as x, okay, or I and j, okay, they weren't like the related to the size of the problem that was n. Okay, so no matter what's going to be the size of n, we only have like a few number of variables or space that required for for solving the problem. So we call the like the insertion sort an in-place sorting algorithm, okay, and because the extra time space complexity for solving the problem is from theta of 1. Okay, so we'll see later that there are some algorithms that they need more extra spaces, okay, but in the insertion sort, okay, we only need that array of size n, okay, so that's going to be our input, but our extra spaces going to be from the theta of n, so that's why we call it an in-place sort.